examples to understand get some insight into the Fourier transform. So this is example 4.1, and we're given the signal xt, which is one-sided signal, and a is some positive quantity. This is e of it's an exponential signal, okay, which is decaying on the positive time axis for the for some positive quantity a, and you can see that xt is both absolutely integrable, and it's also square integrable. Okay, I mean the absolute sum is also absolute sum, and the square of the magnitude is also absolutely integrable. So this will imply that the Fourier transform exists. Okay, and this condition is valid for a being a positive quantity, right? I mean, you can show this for yourself. It shouldn't be that difficult. So this guarantees that the Fourier transform exists. So we have a convergent Fourier integral for that, implying that x of j omega exists. Okay. Now, so what is xj omega? Now, if you recall what we discussed before, xj omega represents the envelope of Fourier coefficients, right? I mean, for example, what we did in the last example was, suppose you have a, let's say, a rectangular pulse, which exists in time from, let's say, minus t1 to plus t1, okay, and this is an aperiodic signal, call it xt, okay, and this is all what we have in the time domain, okay. Then if we want to create a periodic version of xt, call it x tilde of t, okay, so this comes with the sign of x hat of t, which is also existing from minus t1 to plus t1, okay, and the center is the 0 origin, and let's say it has a period of capital T, so this is minus t by 2 to, let's say, plus t by 2, and then the same thing is going to repeat itself at plus minus t, plus minus 2t, and this trend continues, okay, on either side. This trend continues, okay. So it's a periodic signal. X tilde t is a periodic version of xt, basically. That's what it says, okay. Now since x tilde t is periodic, we can argue that we can represent this in terms of Fourier series with Fourier coefficients being AKs, which are the strength of the harmonics. Which harmonics? These are the exponential harmonics. Okay, these are the complex exponential harmonics, which are related by k omega naught being the fundamental frequency. So this is jk omega naught t. Okay, so you can see this summation is over k. So for k equal to 0, we have the DC term. Then for k equal to plus minus 1, we have the first, or the fundamental frequency, plus minus 2. It's a second harmonic, and this trend continues. So xt being periodic, x tilde t being periodic, is we should be able. There's no reason why shouldn't be able to represent this in terms of Fourier series, given that this periodic signal is it has a limited number of, it has just two discontinuities, basically. It has two discontinuities in one period, and those are also finite. Okay, it's absolutely integrable, so the series is convergent in that sense. It satisfies the Dirichlet's condition, so Fourier series is convergent. Fine. Now, what is the relationship of AK and x of j omega? Okay, so let's try to recall that intuition. Okay, because it's very straightforward. You go ahead and just plug in the Fourier integral. You plug in the signal in the Fourier integral and say, okay, well, look, this is the transform. Well, what is the intuition behind that? What is this expression? What does this expression shows you? What does this expression represent? What is the insight? Okay, so let's try to understand. Let's try to recall the intuition behind the Fourier transform over here. So what we are trying to do is, since we say that x tilde t is the periodic version of xt, so we should be able to express this in terms of Fourier series, right? And when does x tilde t becomes equal to xt? Well, that is when the period, let's say capital T, becomes infinitely large. Okay, it becomes infinite itself. Okay, when the period becomes infinite, xtilde is an accurate representation of becomes an exact representation of xt. So in that manner, the Fourier coefficients of xtilde by definition are given as, if you recall in chapter 3, the Fourier coefficients are xtilde. You do this over one period, right? I mean, you have to do this. So this is, you take the average 1 over t, and this integration has to be done over one period. So you can do this from minus t by 2 to plus t by 2, okay? And then you have e of minus j k omega naught t, okay? So that's what it is. Then what you do is, well, if I have to integrate this in one period, so let's say from minus t by 2 to plus t by 2, that's one period. Then you see in this period, this is the range, right? I mean, we are talking of this range of time, okay? So this is actually minus t by 2 to plus t by 2. In this range, these both signals are the same, right? I mean, xt is x tilde t over one period, right? I mean, for t being less than equal to t by 2, both signals are the same. Therefore, there is no difference. I can remove this tilde and I can write this as 1 over t from, well, let's put the limit afterwards. So this is xt e of minus j k omega naught t, right? That's my, and then I'm forgetting about dt, okay? There's dt as well. So the integration variable is time. So either I can integrate this from minus t by 2 to plus t by 2, there's no difference, or I can put in general the limits minus infinity to plus infinity, okay? Does this matters for an infinitely large periodic signal or aperiodic signal? So for xt, I mean, integrating it from minus infinity to plus infinity is the same as integrating it from minus t1 to plus t1. That's where xt is existent. It's non-zero, right? So that's in general is the case. Now this expression implies that t times of ak is the quantity that I have the integral minus infinity to plus infinity xt e to the minus jk omega naught t, right? So, and you see, the next reason is that if t becomes large, well, if t becomes large, then in that limiting case, x tilde t becomes equal to xt, right? And the Fourier series representation of x tilde t, it has to be an aperiodic representation, right? I mean, forget about periodicity now if t goes to infinity. So the first consequence over this expression over here is that your omega naught becomes infinitesimally small, that is, which is 2 pi by t, it tends to 0. If t goes to infinity, then this expression, the omega naught, should go to 0, right? And in that case, the harmonically related exponentials, they bunch together. Therefore, you will have a continuum of the envelope, if I may express this as x of j omega. If I can express this as j omega, where my omega over here is not discrete, okay? I mean, my omega is a continuum because omega naught is a very small number, and this k is where k are the harmonic indices, okay? I mean, k is 0, it's plus minus 1, plus minus 2. It's the harmonic components are very close to each other, right? They become very close to each other, and there are a large number of samples which exist. So these samples for xj omega, so you see the large number of samples are going to produce a shape that will look like a continuum of what? Of omega, right? Omega is k omega naught right now. So I will rather have an envelope whose samples are AKs. So what this xj omega is representing, xj omega, you see this integration is again, it's a very similar form, xt to the minus j omega t, where omega is k omega naught. So omega, k omega naught has been replaced by omega, which is a continuous function. Therefore, xj omega happens to be a continuous function, but its samples, okay? So its samples will be the Fourier coefficients, ak, which are the strengths of the corresponding harmonic components or the frequency components that are contained in xj omega. So in other words, if you see xj of omega of this form, well, that simply means that the samples are the Fourier coefficients AKs, or you can say alternatively that they are the Fourier, they are the strengths of the frequency component contained in the um, function x of omega. Okay, so x of omega is simply showing you how the frequency is distributed in a signal. Okay, that won't be wrong to say. So TAK represents the now TAK is being represented by the envelope, which is continuous in omega, and that envelope happens to be xj omega, which gives the frequency distribution of the signal. For example, for this particular configuration, we can see that more strength is concentrated at DC, right, instead of high frequencies, right? So so low frequencies are predominantly contributing more strength to XT. Now, far as the analysis is concerned, fine. I mean, you can drop this xt into the definition over here, and this xt is one-sided, so the integration starts with 0, goes to infinity because of ut, right? And then you can combine these two exponential, you can come up with an expression, put the limits, and that's your xj omega. Okay, where a is a positive quantity. Now note that xj omega is complex, right? If it is complex, then naturally it is going to have magnitude part and the phase part. So if you look at the magnitude part, again, you see that the samples over here, again, which are the strengths of the frequencies. Okay, so these are the strengths, because one more thing you see over here besides the frequency distribution is that the Fourier transform is both symmetric and well, it is symmetric. Why it is symmetric? Because your xt is a real signal. Okay, xt is a real signal. So for real signal, the Fourier transform is even and symmetric. So you see over here, x of j omega, the magnitude response j omega is equal to x of minus j omega. So the Fourier transform is symmetric. The magnitude response is symmetric. Okay. However, you will see that the phase response is an odd function of omega, while magnitude function is an even function of omega. That is, if you take the phase, you consider the phase, this is the odd function of omega, right? So the phase function is an odd function of omega, while the magnitude function is an even function in omega, and it is symmetric. Why it is symmetric? Because your signal is, we're dealing with the real signal. Okay, so since the Fourier transform is a complex valued quantity, so to plot it as a function of omega, we express xj omega in terms of magnitude and phase. So this is the magnitude, and you can see as omega tends to infinity, your magnitude response is dropping, right? I mean, the magnitude response is dropping. So high frequencies are not much contributing. It's a low pass signal. Basically, the frequency content that it has is predominantly is more dominant around DC. So it is, you can say that this is centered around DC. Okay, and the phase response is given by minus tangent of omega over a, and you know that tangent function is an odd function of is an odd function. So phase response naturally comes out to be odd in omega. Okay, so note that a is a complex rather than real quantity. No, okay, note that if a, we consider a as a real quantity, but if a was a complex rather than real, then xt is absolutely integrable as long as the real part of a is greater than 0. Okay, which was the case before as well. And in this case, the preceding calculations yields the same x of j omega. Okay, so if the real part, even if a is complex and the real quantity of A is greater than 0, then xt is again absolutely integrable. Therefore, it guarantees that xj omega exists, and it's of the same form as earlier we have seen xj omega for A being a real quantity and a real and positive quantity. Okay, we assume that. Okay, but it could be uh, if it is imaginary, then again we have the same form because xj omega exists because again xt will be absolutely integrable for real part of A greater than 0 in case it is complex. So you see in both cases, um, unless up until it's absolutely integrable, the Fourier transform exists. Okay, and if the Fourier transform exists, it is complex, then we have both the uh, magnitude and the phase responses as well. Okay. Now we have another signal. This is example 4.2, right? And the signal is two-sided. Okay, this is E minus A, where A is again a positive quantity, magnitude of T. So T is it's there on both from minus infinity to plus infinity. It exists. All right. So if you carry out the integration, you have to bifurcate into two integrals, so minus infinity to 0 and 0 to infinity, because there is no ut or u minus t with it. And if you combine these two integrations, this integration is very similar to what we have seen before. So this 1 over 1 plus aj omega is there from the first example 4.1. So if you combine them, you have a real Fourier transform. Okay, it's not imaginary. So it's very easy to see that the envelope of xj omega, once again, as omega tends to infinity, the frequency content is predominantly low. Okay, I mean you have the strengths of the low frequencies are greater than the strengths of the high frequency. So high frequency is not much contributing into the signal power. Okay, signal power is predominantly low frequency. It's a low frequency content that is there. Okay, now since xj omega is real, well, the phase part is 0, right? The phase is 0, so we are not considering any phase over here. All right, so let's consider another simple function, delta t, basic function delta t. So if you want to determine its Fourier transform of the unit impulse, you plug this into the definition of Fourier transform integral, and you see that this ej omega t becomes e minus j 0 t, which is 1, and delta t dt by definition is 1. What does this mean? This means that delta t, which only exists at t equal to 0, and this is 0 otherwise, will have a Fourier transform pair with a constant, and that constant happens to be 1 for all frequencies. Okay, so this basically this thing continues over the frequency axis on either side, right? This means that if you take the samples, if I have to take the samples on either side, so let's say omega naught, 2 mega naught, 3 mega naught, all the frequencies are contributing the same power, right? I mean, all the frequencies have the same magnitude. Therefore, it's just like the spectrum of a white light, where all the visible spectrum is contributing to make it white, right? Okay, so I mean, you have all the colors that make it white, basically. So unit impulse has a Fourier transform consisting of equal contributions at all frequencies. So there are equal contributions for all the frequencies. Now consider a rectangular pulse that we have considered, that we actually considered in example 3.5 as well previously when we discussed Fourier series. Now what we have done is that we have made this an aperiodic signal because its period capital T has been considered to be infinitely large. Okay, so as shown in figure 4.8a, this is 4.8a, this is a rectangular pulse, example 4.4, and we apply the Fourier transform, and you see that the Fourier transform, the envelope, has a very similar relationship to what we have. I mean, it's exactly the same as TAK. So it's the envelope of TAK, okay, which is the Fourier coefficients, which means the samples of the Fourier transform are the Fourier coefficients AKs, okay, and irrespective of how large T is, the shape of the envelope is that of a sinc function, right, with a main lobe width of 2 pi by T1, and well, whatever is the value of capital T is not being affected. It's not affecting the shape of this waveform as discussed earlier. Okay, the shape is still the same, right? With the main lobe width, certain main lobe width, and side lobe heights. So the waveform stays the same, right? I mean, it does not depend on capital T, how large the period is. And you see, these are basically the Fourier. I mean, how can you express A case? If you want to write the Fourier series coefficients for that, this is 1 over T x of j omega, okay, where omega is, what is your omega? Omega is k omega naught, okay, with T naught being infinitely large, basically. T is large, okay, so omega naught is small, okay, so T is large, omega naught is small, so it becomes a continuum. I mean, this omega will be a continuous function, right? Because k omega naught, the harmonically related Fourier coefficients are much spaced closer together, okay? They become bunched together. Then an interesting, well, an interesting thing to notice over in example 4.5 compared to 4.4 is what you see is that now xt, the form of the xt was a rectangular pulse. Now, if you have the same form in the transform domain xj omega, then by duality property of Fourier transforms, xt will be a sinc function. Okay. So what the duality property says is that if xt, we'll talk more about this in upcoming sections. If xt is a Fourier transform of xj omega, and if xj omega is, if xt is such that it satisfies the Dirichlet condition such that xj omega exists, then it has to be unique. So you can take the inverse Fourier transform and find xt, right? Then that means if the time domain function takes the form of the same form as x omega, okay, capital xt, then in the transform domain, so I'm for the transform, I'm just indicating this by capital X, okay. So in time domain, if it's the same function, capital X, okay, it's just a function of time, then it will have a Fourier transform of 2 pi small x, same waveform as it was there in time, minus omega. So you see, flipping does not matter in transform domain, but that the duality principle says that if you have a rectangular pulse in time domain, its Fourier transform is a sinc function. But now if you have a sinc function in time domain, like you have it over here, if you have a sinc function in time domain, then its Fourier dual will be a rectangular pulse in frequency domain. Okay, so that's duality. That's duality. So again, xj omega is defined as a pulse. Okay, in frequency domain, the pulse width is set by 2w, right? And if you want to show this mathematically, well, you can just plug this expression into the inverse Fourier transform relationship. You can find xt as a sinc function. So this is a sinc function. Well, sinc function, definition of sinc function is, as defined in text, is sinc theta is basically sine of pi theta or pi theta. That's how it is defined. For more information on sinc function, you can just read about sinc function. They're important because we're going to deal with them a lot in signal systems, and when we are going to have a look at the systems, the transform analysis of the systems, and then further on we are going to in your communication systems courses, you will see a lot of the sinc functions. So you must understand what is the main lobe width and how side lobe heights are being affected, given the pulse width, for example, what happens on the main lobe height, what happens to side lobe height. So this is the basic formulation. You can read more about the sinc function in section 4.2 of Oppenheim and Schaeffer, okay, the course text. So this is depicted in 4.9b, and this is a sinc function. So that's all.